Okay, we're going to start the year with a little bit of algebra review, speaking specifically of linear functions and relations. And we're going to start that off by talking about ordered pairs. Ordered pairs typically come in a form of x and y, an input and an output value. And those can then be graphed to a corresponding position on the horizontal and vertical axis in the coordinate plane. So if we had, say, an ordered pair of 4, 2, that corresponds to 4 over on the x-axis and 2 up on the y, and would be placed right there. Additionally, we have what's known as a relation, which is really any ordered pair or any time that we have an input of an output, be it x or y, h and k, anytime there is a connection between two things, we have a relation going on. And then we have the domain, which is the set of all typically x values when we're dealing with ordered pairs, x and y. And then the range is the set of all y values. So if we look at the example below here and look at the data table of wind chill factors at 20 degrees, we're asked to list ordered pairs, graph, and state the domain and the range. So I see I have a relation here. I have a wind speed and a corresponding wind chill, and this is also the ordered pair. So I have 5, 6, 10, 7, 15, 2, 20 and 1, 25 and 0. And I'll go ahead and put those on my graph here. And so I have 5, 6 is my first. So 5 over, 6 up. Then I have 10, 7. I have 15 and 2. It's going to go off my graph here, but that's fine. We'll say 10, 12, 14, somewhere in here, 15 and 2. 20 and 1, so that's somewhere down here, and then 25 and 0. So it looks something like this if my graph continued out. And giving the domain and range is pretty easy. If I list them like this, I have all of these for a domain. And we'll list those over here. We use these brackets to do so. And we list them in order from smallest to largest. So 5, 10, 15, 20, 25. And if there were any duplicates, we would not duplicate them when giving the domain. And then we'll list the range, which is just these y values. Again, you list them in order so they don't necessarily correspond to one another. So that would be 0, 1, 2, 6, and 7. And so we have the domain and range. A function is simply exactly one y value for each x value. So what that means is when I plug in a number for x, I only get one output, one y value. And then we have a one-to-one function, which really just takes it one step further, which means that it is a function. So there's one y value for every x, and then there's also, so we'll say above, we'll just quote it here. And then also, so plus, there is one x value for every y value. And you probably remember from Algebra 1 or Algebra 2, when you had a function test. Very simply, if you had a graph, you did what was called the vertical line test. And you just simply drew vertical lines or looked to see, do any of these vertical lines cross my graph more than one time? That was a function check. And then to do a one-to-one function, similarly, we do the vertical line test. So I draw these vertical lines to see if they cross my graph more than once. And then we also do a horizontal line test. And if it passes both of those, we would know it's a one-to-one function. So if I look at this set of points here, I see I have a relation because I have pairings of values, x and y. I have an input and then I get an output. So the domain and range, we'll set the domain, which again, this is the x values. And I'll list them in order. So in this case, I move from left to right, the low to the high. And then I'll list the range, which is the y values. And this I'll list from bottom to top, low to high. Is this a function? Well, I can look at either my domain and range, and is it a function? Do I see any repeating x values? Maybe another thing you learned in Algebra 1, no repeating x values to determine a function. And I see that I do not. So yes, it is a function. There is one output for every input. And if I were to do this, say, with a vertical line test, I can see that there are no 2 points on any one given vertical line. So that passes both of those tests. We've already referenced the vertical line test. You just saw it above. And if I were to extend that here on these graphs, and I just draw my vertical lines, or I can imagine it, and I see that this only intersects the graph at one location on any one given vertical line. So this is a function. You'll see this one, however, this vertical line is going to intercept my graph here, 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 and here. So anytime I have an input of, say, make it 0, right here on the y-axis, I see I have a point of intersection here, here, and here. So I actually have 3, and this would just continue on to snake around. So I have an infinite number of possible outputs, so this would not be a function. But again, a simple vertical line test is all it takes to determine that. We see the same thing here with the graph of a circle. Intercepts here and here, so this would not be a function. Function notation you also learned in Algebra 1. It's really just a different way to write the most common of y equals. And the parent linear function would just be y equals x. And you were shown then that we could also express that typically as f of x, although you could really use any characters that you wish. What this means is this is a function of x. You would say this is f of x. So it's the function f at the given point x. So in order to evaluate these for the following functions, I have f of -1 if f of x is negative x cubed minus 1. And the easiest way to think about these is look at the characters that you see. So I have the function notation here of f of x, but I'm needing to evaluate it at the point -1. So here's my input. So I need to find the function of x when x is -1. So you'll see that the -1 has really taken the place of the x. So where I see the x here, I just have to substitute the -1. So I have negative x cubed minus 1. It'll be a big aid to you if you go ahead and keep your input in parentheses. That's going to help you keep your order of operations and the structure accurate. So as I begin to evaluate this, I have -1, and that value is going to be cubed. So it's -1 times -1 times -1. I know that the negative cubed is going to come back a negative. And then I multiply it by the negative, so it flips it to a +1, subtract 1, and I get 0. And when I evaluate f of 3, if f of x equals the absolute value of 3x squared, again, I'm evaluating this function at x, where they have now told me to evaluate it at 3. So I take 3 here, substitute it in for the x, so I replace the x here with 3. So the absolute value of 3 times 3 squared. So again, use your parentheses, and that's going to help me. I see that the 3 is first squared, so 3 squared is 9. 9 times 3 is 27, and then the absolute value of that is 27. And then I have g of m, if g of x is 2x to the 6th minus 10x to the 4th plus 5. So I'm going to go ahead and replace this everywhere I see an x. I'm just going to go ahead and replace it with a 4. And I don't have to use the parentheses right now because I cannot evaluate this any further. It's ultimately been simplified. So I have 2 m to the 6th minus 10 m to the 4th plus 5. So I can't take this any further because I've replaced a variable with another variable, an unknown value. And then in this case, h of the quantity a minus 2, if h of x is equal to 2x squared minus x plus 3, we do the exact same thing. It's no different wherever I see x in here. So you can put boxes around them. I just take what's in this box and replace these boxes with that. So I have 2 times a minus 2 squared minus a minus 2 plus 3. Well, when you have this binomial, or this two-component term here, you're going to have to FOIL this here where it's squared, and then distribute through the negative here. So a couple extra steps here. So I'll rewrite this as 2 a minus 2 times a minus 2 because it's squared, minus, and I'll just distribute this through a minus a negative 2, which is the same as plus 2 plus 3. So we see these two can be combined. The first thing I'm going to need to do here is either distribute this and then FOIL these. I'm going to go ahead and I'm going to do that. I'm going to distribute this through. So that's going to get me, I'm just going to come over here to the right, 2a minus 4 times a minus 2 minus a plus 5. And then I'm going to double distribute or FOIL these out. So I have 2a squared minus 4a minus 4a plus 8 minus a plus 5. And then we just combine the like terms. So this is my only squared term, so 2a squared. Then I have minus 4a and a minus 4a, that's minus 8a's, plus 8a's, we'll see those cancel, plus 5. So ultimately I'm left with, I'm going to go back up top here because I'm running out of room at the bottom of my screen, 2a squared plus 5. So it's just some simplification there. And we'll close down to the final section. Talk a little bit about domain restrictions. Domain restrictions occur when we cannot solve or we have no possible value. If you were thinking of it in terms of input into a calculator, it will error out. It will get you that go-to error in your calculator. And that's going to primarily occur if you're told that there's a domain restriction given the context of a problem. Perhaps certain things may not make sense, like negative time components would be a restriction on your domain. You're not going to go back in time into the negatives, so you can only end at 0. But when you're given a function like these below here, f of x equals x squared plus 2x over x minus 1, when you have this rational function, you're going to get domain restrictions when you end up with zeros in the denominator. Remember, we can't divide by zeros. If you do it in a calculator, you're going to get that error. And that's what I'm talking about here. What you'll see on a graph is this will actually create asymptotes, which is something that we'll talk about later on. But in order to find the domain restriction, all you really have to do is set the denominator equal to 0. So all I want to know is when is this function going to error out? And that's going to happen when this denominator, the quantity down there, x minus 1 equals 0. So I rearrange this to figure out what value of x is going to make that happen. And I see that's going to occur when x equals 1. So in order to state the domain of this value, I can use my set builder notation, say it's the set of x such that x is equal to all real numbers except, and we can use just like a not or not equal, x cannot equal 1. So some different ways in which we can notate that. Or you can say all real numbers, it's just your r with an extra backbone here, x cannot equal 1. And oftentimes you'll find that people just put x cannot equal 1 for the domain of this as well, implying that it's all real numbers except 1. And we can do the same thing with this one. However, I have something that's squared. So the first thing I want to do is I look to factor that. So x squared minus 4. And we should know that that's going to be our difference of squares. So this actually factors out to x plus 2x minus 2. So this is going to occur when these two equal 0. And I know that x cannot equal negative 2 or 2. And for our purposes, I'm content with just stating this, implying that we know that it is all real numbers except for values, or that I will get errors or domain restrictions at negative 2 and 2. Well, I hope that refreshed some of the concepts from Algebra and Algebra 2 that you've already discussed. Come to class prepared with your notes, and we'll get a little bit more practice out of the book.